It's special for you.
Right.
Not that it'll come out of the ceiling.
And then the apple goes on the head.
Right.
All right, so, hi everybody, thanks for being here. We have a group of four guys with a really neat device that will hopefully help out one of our corporate sponsors and local industry in town with their designs. I learned quite a bit about how far advanced we are above what would be Paleolithic man with his bows and arrows. This is some pretty high-tech stuff. But I'd like to hand it over. Tyler, Ethan, Logan, and Derek. There's an acronym that goes along with that, but that's not important. On the bow shooting machine. So thank you, guys.
Thank you, everybody, for coming. As Dr. Field stated, I'm Tyler. This is Logan, Ethan, and Derek. Our advisor for this was obviously Dr. Field. The liaison is Josh Sidebottom from Bear Archery. And we'll be presenting on the bow shooting machine.
Today we're going to talk a brief outline over what we're going to cover today. We're going to begin with the objective of this project, and then the problems that Bear Archery currently is faced with, a little bit of background on Bear Archery itself and archery as well. We'll roll from that into current testing operations that Bear Archery performs to gather information about current bows. We'll move on into the design requirements that they laid forth for us. From there, we'll break down into the components that we designed and the programming that we did to accomplish these goals, and we'll finish it off with a budget of what we spent on this project. So the objective of this project was to design, build, and test a machine, an all-inclusive machine capable of shooting a bow accurately and precisely, while also collectively measuring a variety of parameters. Currently at Bear Archery, when they test bows, they currently use a variety of machines to gather the information that they need. And the issues with this is it can lead to variation going from machine to machine, and also going from machine to machine, it takes time to set up each machine individually. So an individual machine will have a large setup time, and then when you accumulate all that together between a handful of machines, the time grows as well. And now the background on archery. Archery is defined as the art, practice, or skill of propelling an arrow with the use of a bow. In the past, historically, archery is used for hunting and combat, and in more recent times, it's still used for hunting, but it's also used for recreational activities as well as competitions.
All right, now we'll go over a little bit of the background of the bow for those of you who aren't familiar with the bows. The scope of this project lies under the compound bow. That's the modern bow that most use today. Bear Archery produces compound and traditional bows. Like I said, the scope of this project is under the compound bow. There's several components that each of these have listed. One is the riser and handle. Attached to the riser and handle are a pair of elastic limbs. The limbs store energy that the archer inputs by drawing back the bow with a string. You have three. And then finally, fourth, you have the grip, and that's where the bow is held. Similar on the traditional bow, the same component, except traditional bows are usually machined or made from one solid piece of wood. The limbs and the riser are all connected together. The string is pulled back and the limbs are bent and the energy is input that way. Unlike the traditional bow, the compound bow has a set of cams. The set of cams the purpose of the set of cams is to help the archer not hold or not sustain the full load that they're pulling back at the end of the draw cycle. So they'll pull the bow back and won't be holding the full weight of the load. A bit of background on Bear Archery itself. Bear was founded in 1933 by Fred Bear. He started producing bows as a hobby and then for acquaintances and friends. Then it got into production. I think in the 70s, production moved down to Florida. Fred actually was with the company until his death in the 80s. Currently, Bear is a subsidiary of Escalade Sports, and the headquarters is here in Evansville, and R&D and all the business affiliation is here in Evansville. Production is still in Gainesville, Florida.
In the next few slides, we'll talk about the current equipment that Bear Archery currently uses in their testing facilities. The first one is the Hooter Shooter. It's a manually operated bow shooting machine that is capable of shooting a bow accurately and repeatedly. downrange to a target at a specified range. What makes the Hooter Shooter unique is the universal bow holder, which implements the capability to accommodate high and low wrist gripping methods. The bows in the past were made with risers that promoted the use of the high wrist gripping method, which is seen in the bottom right. It said that the least amount of surface area of the palm that you have on the grip will apply the least amount of torque. You want the smallest amount of torque in each shot because you don't want the point of impact of the arrow with the least amount of deflection downrange. In modern bows, the risers are made to promote the low wrist gripping method, which is on the left. It is the easiest to repeat and is the most efficient. The Hooter Shooter itself has certain limitations. For one, it lacks automation because it has to be drawn back via mechanical hand crank and also released via mechanical hand-operated release. It lacks rigidity due to the vibrations of each shot. Therefore, it could be bounced off the point of impact between each shot. It has a slow setup and operation time, which many of the machines that we'll be covering have a slower setup time, and we're trying to alleviate that with our all-inclusive machine. The next piece of equipment will be the draw board. It's used to get a rough estimate of the draw length and also the draw weight. As you can see in the background of the bow, it has a ruler for when the bow is drawn back via a hand crank. You can get a rough estimate of the draw length, and the scale at the top will give you a rough estimate of the draw weight. Again, the limitations of the draw board, it is not automated, so it's all done by hand crank by the tester themselves. It requires excessive setup time, and also the data must be transferred from this machine into an overall summary spreadsheet, which will be put in later. And for the draw board, once this test is completed, it gives you a rough estimate of the draw force and the letdown curve, which is then put into the next machine that can be tweaked. So the third machine that they use is the Instron test machine. As can be seen on the left, this test machine can be used for tensile or compression properties. Bear Archery uses it mainly for tension or tensile properties, where the bow is pulled back. On the left at the top of the picture, the riser or the handle is connected via a wire to the moving portion of the Instron, which is the carriage. And as can be seen on the right, which is a zoomed in portion of the bottom left picture, is the bowstring connected to a shackle, which is then connected to the load cell. And the load cell will be able to map out the draw force and the letdown curves. Limitations of this piece of equipment, which is the Instron, has excessive setup time once again. The data must be transferred from the Instron machine to an overall summary spreadsheet, and the bow can possibly be set up off-center. If you see the D loop, which is circled in the picture on the right, it is where the arrow will connect to the string and will then be released by the mechanical release.
As Logan had mentioned the draw force curve, we wanted to go ahead and iterate what the draw force curve is and its importance. We'll go into more depth later in the presentation, but as you can see here, there's a graph. On the y-axis we have the draw weight. That's the force required to pull the bow back. And the x-axis, the draw length, that's the length of travel that you've pulled the bow back. So as the bow is pulled back, the weight increases, and there's an area under the curve that's designed. This input energy is useful for helping design the bows, and it's just useful for gathering lots of different types of data in the test and R&D environment. The right-hand side is the letdown curve. It's roughly a mirror image of the draw force curve. There are a few things that cause it to be lower that will be discussed later.
Bear Archery came to us with a few design requirements. Their requirements were stated as, it shall be a single contained unit, it shall shoot the bow accurately and repeatedly, it shall graph the draw force and letdown curve, which Derek just explained, as well as measure the vibration in the shot, the noise in the shot, and measure the strain on the limbs. This is our current SolidWorks model. This is kind of how we derived or came up with our final actual model that we would be finalizing. Some of the integral parts, very innovative release mechanism we'll get into in a future slides, as well as the grip holding method for this bow. Now we're going to go into a system breakdown. This system breakdown will be of the shooting machine and the physical components only. First, we'll go ahead and start with the testing stand. The testing stand, we decided to go ahead and use 80/20 extruded aluminum. We chose this option due to its strength, rigidity, and lightweight abilities. That being said, it also needed to be mobile, so we were able to put casters on this and they locked as well. Then, going about it, we needed some way to mount everything, so we came up and decided to use aluminum plate for the top.
Okay, the second piece of the system breakdown, we're going to be talking about the drawing mechanism. That'll be the linear actuator that I'm holding now. We chose to buy this from Specialty Motions Incorporated. It's called an XLA 15 ball screw linear actuator. We paired the linear actuator with a NEMA 23 heavy duty servo motor that has a travel life of roughly 2 million inches. And it's used to draw the bowstring back smoothly in order to get our draw force and letdown curves. It has a static load, so a weight can be set on this top plate of more than 14,000 pounds. And when the linear actuator is in motion, it can move up to 9,500 pounds. Bear Archery put a requirement of at least 500-pound draw force and 30 inches of travel within the linear actuator.
The next component we're going to talk about is the release mechanism and the grip that the bow is mounted into. As you can see on the left, the release mount, this whole assembly mounts to the carriage on the actuator. At the rear of it, you can see it has horizontal and vertical adjustment knobs, and that's to accommodate any different bow that might have variations in the grip. It also will allow for a few inches of adjustment to possibly aim the bow if that is desired. Next, that goes into the load cell, and as Derek and Logan both mentioned, the load cell is used to collect data for the draw force and letdown force curves. Next, that goes into mechanical bow release. That's what is connected to the string on the bow, and the operator of this machine will manually release the bow using this release. And on the other side, you can see the bow holder, which is what is actually holding the bow itself. This is made out of Delrin, a hard plastic, and it has a unique geometry that allows it to accommodate the high or low risk grip methods that Logan has spoken about. And the contour of it also allows any bow to become centered in it as it is drawn back. And next we get into the systems breakdown for the software and electronics. With all these requirements for measuring data and collecting data, we wanted to come up with a system that would integrate well and be fairly easy to operate and adjust. We decided to go with NI or National Instruments components because they seem to have the best working method between all the different types of sensors we require. So first off, the main component is the 4-slot chassis. This chassis hooks directly to the computer, and that's where all the LabVIEW programming is done. This chassis accepts all the different types of modules for acquiring data. So then we have the modules which we selected. We have the strain module, and the strain module is used for collecting the data from the load cell and the strain gauge. And we have the voltage module. The voltage module is used for collecting the voltage and data, the input-output data from the linear actuator. And then finally the IEP measurement module, and that's for the accelerometer and the microphone. Here we'll go through the components so you can get a visual. This is the 4-slot chassis. As you can see, the modules, the voltage, IEP, and strain module, they all interface with this 4-slot chassis we plug in. So we have our components that we plug in to the modules, and then the modules plug into the 4-slot chassis. That way everything's interfaced into one program. On the right, we have a PCB signal conditioner. The signal conditioner's purpose is to convert analog to digital signal, and that's needed for the microphone and the accelerometer. For the component integration picture of our actual testing setup, which we have over here on display, you can see again the 4-slot chassis, the voltage module, the IEP module, and the strain module. And here's a picture of our preliminary sensor testing. We wanted to test everything as early as possible as we got all the components in, so we could be sure we were on the right path with our programming and had the right components and hardware to meet the requirements from Bear Archery. So we went ahead and used the Hooter shooter
right track. And all this is prior to getting the motion system in from Specialty Motion. Picture of the data acquisition sensors. On the microphone, we set the microphone up for this testing. It was loosely set up, close to the bow, as close as we could get it without possibly falling off or damaging it. We didn't want to hard set any of the components in because this is just for testing. Then we have the load cell. The load cell was hooked up similarly to the model that we saw previously. It was statically mounted on the hooter shooter and then attached to the release that was attached to the bow string. And then finally the accelerometer. The accelerometer is placed on the bow's riser, the handle. That is placed close to the grip to emulate or to sense the feeling that an archer would have when they shoot the bow. We want to measure the vibration that a person shooting the bow would feel. So that's why it was placed right there by the grip.
All right, next we're going to get into a little bit of LabVIEW. LabVIEW is the main program that we decided to go with, simply because NI supports that program. In doing that program, this looks quite confusing. I'll try to break it down as easily as I can. The data acquisition symbol, which Derek is pointing to now, that is the 4-slot chassis, or where Derek was explaining where everything is plugged into. It's actually right here, and this is pretty much what plugs into the computer. And we use LabVIEW to integrate this system and get everything to mesh together. From this data acquisition, we had to split the signals. We went with 3 different signals because at this time we had the accelerometer, microphone, and load cell. So that being said, for the load cell we used the strain module. For the accelerometer and microphone, we went ahead and used the IP module. From this data, we were able to graph it on an XY graph. We got the data and we were testing and things like that. The issue we were running into is we weren't able to correlate the time that the XY graph was getting and the distance that we were pulling the bow back. So for the draw force and letdown curve, it was being difficult to get that. So as you can see by the orange lines here, basically that's just putting in the current time and a time step to be able to get an accurate measurement so we can correlate the time with the distance.
So for the XY waveform graphs that Tyler had just explained, we had the force curve from the load cell, the acceleration curve from the accelerometer, and also the microphone, or the sound wave from the microphone. We did 2 distinct groups. We have the 3 on the left from the undamped bow test. That is when the bow or the string stops or moved out of place, and the string is able to oscillate frequently after the bow is shot. The 3 on the right are from the damped bow test, so they were put back in place and shot again. Therefore, the strings will hit the string stops and will no longer oscillate as quickly. So we're going to zoom in on the acceleration waveform graphs from each test. The one on the left is from the undamped acceleration. You can see that there's a second oscillation that Derek is pointing to now. It shows that the string was able to oscillate after the shot of the test. The damped acceleration slowed the oscillations down and brought it back down to 0 at its normal resting position. And we did notice that we had the time scale off on both of these just because we want to portray the size of that second oscillation on the undamped test.
Our final testing, where we verified that the load cell was an integral part in this testing because, as I mentioned before, the draw force curve and letdown curve is very important to bear in an R&D process. So here again, you can see on the y-axis we have amplitude or poundage. For this, it's actually a time variant. It's not a draw length relation, but it serves the same purpose. So we have, as the bow's drawn back, we see a climb in weight. And our peak weight is roughly 58 pounds there. And as you see, as the bow's drawn back further, we go to a minimum of about 18 pounds. This is roughly 70% of the peak force that's required to pull the bow back. That's typical, and that's a result of the cam systems, and that's their importance. And you can see on the letdown curve side, again, it's roughly a mirror image of the right side. Slightly lower peaks, peak of roughly 55. That's due to friction between the strings and the cams. That interference causes a loss of energy on the draw and letdown side.
This is the budget for the project. from PCB as well. And the linear actuator from Specialty Motion was also fairly expensive. The other costs down here at the bottom, the miscellaneous costs, come from the cost of the 80/20 and the mount and the release mechanism and any other components that we have to purchase separately or have machined. This gave us a total cost of slightly under $27,000. This here is, once we got the linear actuator in, we wanted to test it the same as we had been testing all the other equipment. And at this time, we still did not have the release mechanism made or the mount that's holding the bow. They had not come in yet. So we mocked up a system to be able to test the actuator to make sure it performed as we wanted it to. And as you can see here, it draws the bow back at an ideal rate for us, and it's a smooth motion throughout its entire length of travel. And now that it's reached its stop, the code is not running at this time. It's being done manually. It's released by the same manner, and once again, it goes through a smooth motion through its entire distance at a constant velocity, which is very desirable for the draw force and letdown force strokes.
All right, this time we'd like to do a few acknowledgments for our careers here at USI. Obviously, we'd like to thank Dr. Brandon Field, our engineering den mother, Donna, because she's amazing, Bear Archery, of course, and our project liaison, Josh Sidebottom, and then any of our friends, family, or fellow classmates. And now we'd like to take time and answer any questions you guys may have.
Questions? Is Bear gonna buy that?
Bear owns it.
Bear.
They're gonna buy the design.
So this was made for Bear, I mean, they paid for everything up until this point.
You guys have a fourth slot potentially for additional DAC cards, right? Is there anything that you can foresee that Bear might be interested in collecting?
Strength.
And there's potential for integrating a chronograph possibly future that could be used for that as well.
There's also potential for some high-speed integration using high-speed video. It's pretty useful in the R&D process. Again, that's further down the road, but it's definitely a possibility.
Okay.
So what parts are still missing?
The release mechanism, that whole assembly, and the mount that's actually holding the bow, that is not in yet.
And we don't have a bottom plate on the cart yet, like we have the model. We chose not to go with another aluminum plate simply because of the cost. I mean, the top plate is very expensive alone. The bottom plate is just going to be used for housing all the components and everything, all the attachments, and all the wires and bundle of everything. So probably we'll go with a piece of plexiglass or similar piece of plywood. Save on cost.
Any other questions? All right, let's give them a hand.